Hello everyone. So in the last class we saw three-dimensional transformation. In this class we will be seeing about three-dimensional viewing pipeline diagram. So in 2D also we saw a 2D viewing pipeline diagram in which how the object coordinates were converted into device coordinates. So a similar technique is used actually in 3D viewing pipeline also. So let us see. First, what happens is that the 3D object will be in the form of modeling coordinates. So, modeling transformation techniques will be applied on these modeling coordinates, and these modeling coordinates will be converted into world coordinates. So, what are world coordinates? We have already seen. World coordinates are used in Windows. So, we saw that in 2D clipping, right? So, you can see that when we were performing clipping operation, I told you a window will convert the image into a viewport. So the next one, you can see, understand it very clearly. The world coordinates after undergoing viewing transformation will become into viewing coordinates. This is what this world window to viewport only we have seen in 2D. Okay. So after viewing coordinates in 2D, we saw that it was converted into normalized viewing coordinate, then to device coordinates. But in 3D, this viewing coordinate is undergoing some projection transformation. Okay, because a computer is a flat screen. A computer screen is a plane, that is, which is a flat screen, and it cannot display three-dimensional object. No, it cannot display three-dimensional object very realistically. So we need to do some projections. Okay, so this projections transformation will convert viewing coordinate into projection coordinates. We'll see some projection transformations very soon. I have already told you that projection is one of an important concept in 3D geometry, and we will see it very soon in the upcoming lectures also. So finally, the projection coordinates will undergo workstation transformation, and the projection coordinates will be converted into device coordinates. So this is the pipeline diagram in which 3D is converted from its modeling coordinates to device coordinates. Next is, what is viewing transformation? We saw what is viewing transformation in 2D also. It is just conversion of world to viewing coordinates. Okay, so the world coordinates will be converted into viewing coordinates, and this process is known as viewing transformation. So we have two basic steps. First, the diagram, if you see the figure A, this will be the normal coordinate axis, and this will be a different coordinate plane. So any object which is with respect to this coordinate plane needs to be converted into the normalized coordinate plane. So what we do is we just translate this coordinate plane's origin to here, the original coordinate plane's origin, and then we do rotation such that this axis, this y of the viewport will be in parallel with y of the world coordinates. X of the viewport will be in parallel with x of the world coordinate, and z of the viewport will be in parallel with z of the world coordinates. So that is what is written in here. Translate the view reference point to the origin of the world coordinate system. Apply rotation and align xv, yv, zv axis with the world xw, yw and zw axis respectively. Finally, we'll get a figure like this, like in C. So that the object will be in terms of the world and view coordinates itself. So the next one is actually a very important concept in this third unit, which is projection. So projection is actually of two types. One is parallel projection and another is perspective projection. First, let us see parallel projection. So in parallel projection, what happens is that the parallel projection discards the z coordinate, and the projection is done with parallel lines from the vertex. Okay, so they are extended until they intersect the view plane. So view plane is the plane on which the 3D object is projected. Okay, so in parallel projection, we specify the direction of projection instead of the center of projection. So if there is a solid object, each vertices is projected to a viewing plane. So what advantages and disadvantages we have in parallel projection is, parallel projection are less realistic. So this is the disadvantage, but the measurements are exact. So the object's measurement and the projected shadows measurement will be the same. Okay, so that is the advantage of the parallel projection. In this type of projection, parallel lines remain parallel and angles are not preserved. Also, this is also one of the disadvantage, that it is less realistic and also the angles are not preserved. So the parallel projection are classified into many types. One is orthographic projection, another is oblique projection. The orthographic projection is further classified into top, front, side and axonometric. Oblique projection is classified into cabinet and cavalier projection. So we will see each of these types in detail now. So in orthographic projection, the direction of projection is actually normal to the projection of the projection plane. So if you take this as the projection plane and this as the projecting line, if you can see that this will be perpendicular to the projection plane. So that is orthographic projection, which is the projection is actually perpendicular to the projection planes. So the orthographic projection, we saw there is front projection, top projection, side projection. So if the front side of the object is projected in the front plane, then it is known as front projection. Similarly, the top projection and the side projection. So in orthographic projection, the one thing you need to remember is that the projecting line is normal to the projecting plane. So that is all you have to remember in orthographic projection. And next is oblique projection. The oblique projection, what happens is that unlike orthographic projection, the projection is not perpendicular. That is, it will have some angle. Okay, so the angle, based on the angle, the oblique projection is classified into cavalier and cabinet projection. In cavalier projection makes an angle of 45 degree with the projection plane, and in cabinet projection makes an angle of 63.4 degree with the projection plane. So what is advantage of the oblique projection is, we can view the object better than orthographic projection. In cavalier projection, what happens is, the projection which is perpendicular to the view plane, the length will be preserved. So the length will not change for the for the projection which is perpendicular. And in cabinet projection, for perpendicular projection, for the projection which is perpendicular, the size is cut by half. So if the length is 1 meter, the projected side's length will only be half meter. Both the projection are shown in the following figure. So this is cavalier projection, this is cabinet projection. See, only half side is there, and here the entire side will be projected. So next is isometric projections. So in orthographic projection, there is one more known as axonometric projection. An orthographic projection will be called as an axonometric projection when it displays more than one side. See, in orthographic projection, we saw the front side, top side and side view. Sorry, front view, top view and the side view. But that was only one face. So if it projects more than one side of the object, it is known as axonometric projection. The most common axonometric projection is the isometric projection, where the projection plane intersects each coordinate axis in the model coordinate system at an equal distance. So this projection plane intersects the coordinate axis at an equal distance. Okay, so this is what is isometric projection. So this here also the parallelism is preserved. So this is parallel, but the angles are not preserved in isometric projections. So in perspective projection, the distance from the center of the projection to project plane is finite, and the size of the object varies inversely with distance. And the advantage of perspective projection is it is more realistic. Okay. So unlike parallel projection, perspective projection will have a center point of projection. So the distance and angles are not preserved. Okay. And parallel lines do not remain parallel. So they all converge at a single point. Okay. So that point is known as center of projection or projection reference point. So based on this projection reference point, the perspective projection is divided into three parts. One is 1-point perspective projection, another is 2-point perspective projection, and the last one is 3-point perspective projection. So this is the example of 1-point perspective projection. See, and this is the example of 2-point perspective projection. This is the example of 3-point perspective projection. You can see in 2-point perspective and 1-point perspective projection, both directions are given. You might get confused, but this is actually very easy. If you keep a projecting plane here, what will be projected is this part. Okay, and if you keep a projecting plane here, what will be projected is actually this part. So actually what is projected in this plane and this plane will remain same. But in 2-point projection, if you keep a projecting plane here, it will have a different projection than what you keep here. So actually some part of this projection will also come in this this part of projection. So similarly that will happen in 3-point projection plane also. So the last topic in third unit is the Bezier curve actually. So you know all what is Bezier curves. So what are curves. So curves are dots which are not in straight line. So how to define it is Bezier curve is a parametric curve defined by a set of control points. It has 2 points which are known as the end points, and all other points in between determine the shape of the curve. Okay, so this is a simple Bezier curve, this is a quadratic Bezier curve, and this is a cubic Bezier curve. How I am saying that this is a simple Bezier curve is, what happens is between the starting and the ending point, there is one point which lies in the same direction, that is the line connecting the starting and the ending point. But in quadratic Bezier curve, what happens is there is one point which is not in the line of sight between the start point and the end point. So the line bends. So this part is known as a curve, and this is a cubic. So what we can say is, if one control point is there which is out of this line connecting the smallest displacement between P0 and P2, then it is known as quadratic. If 2 such points are there, then it is known as cubic. If 3 such points are there, it is 4th degree polynomial curve. So this is the general representation of the Bezier curve equation. So with this we have completed the third unit also. So till now in computer graphics series we have seen so many things like 2D geometric representation, 3D geometric representation, many display devices like raster scan, random scan displays, many algorithms, line clipping algorithm, polygon clipping algorithm, text clipping algorithm, and also midpoint circle algorithm, ellipse generating algorithm, line drawing algorithm like the DDA algorithm, and the Bressenman's line algorithm. And in third unit we discussed about what is Bezier curves and what are 3-dimensional representation, 3-dimensional transformation we saw viewing for 2D and 3D, and finally we saw what are projections. So with this we have completed the first 3 units of computer graphics. In the next lecture we will be seeing what is unit 4 and what are all we are going to be discussing in unit 4 in computer graphics. So thank you to you all for patiently listening to my lecture. Thank you.